What causes unexpected behavior in electrical prototypes? Imagine building a new electronic device, and suddenly it stops working or behaves strangely. What could be causing this? Let's explore the main reasons behind unexpected behavior in electrical prototypes. When working on prototypes, every component has manufacturing tolerances. For example, a resistor labeled 10,000 ohms with a 1% tolerance can vary from 9,900 ohms to 10,100 ohms. When many such components are used together, these small variations can add up and change how the circuit functions. This can lead to unexpected results, especially in sensitive parts like filters or timing circuits. Another common cause is poor connections or assembly issues. Loose wires, cracked solder joints, or fragile connections can cause intermittent problems. Even tiny cracks that are hard to see can interrupt signals or power flow. These issues often cause components to stop working or microcontrollers to behave unpredictably. Using printed circuit boards instead of breadboards can help reduce these connection problems because they provide more stable and reliable contacts. Manufacturing defects also play a big role. During printed circuit board fabrication or assembly, errors like misaligned components or solder bridges can happen. These defects can create unintended electrical paths or open circuits. Such issues cause current to flow incorrectly, which can damage the device or make it behave erratically. Environmental factors are also important. Changes in temperature can cause the circuit board to expand or contract, which might damage solder joints or warp the board itself. Moisture and humidity can lead to corrosion or the growth of conductive filaments inside the circuit, causing shorts. Dust and dirt can block cooling and lead to overheating, which damages components over time. Electrostatic discharge is another factor. Static electricity can damage sensitive parts like integrated circuits during handling or operation. Even small ESD events can cause immediate failure or latent damage that shows up later as strange behavior. Software and firmware interactions with hardware can also cause surprises. Embedded software that is tightly coupled with hardware might reveal bugs only during real-world testing. Timing issues, such as mishandling hardware interrupts or missing critical timing windows, can cause sensors to respond unpredictably or communication between chips to fail. Incorrectly initializing peripherals like analog to digital converters or communication interfaces can also lead to strange prototype behavior. Design and layout choices matter too. The way the printed circuit board is designed, including trace spacing, hole sizes, and copper thickness, influences reliability. Poor design can make the circuit more susceptible to issues like crosstalk, signal integrity problems, or electrochemical growth of shorts. In practical testing, thorough documentation and inspection of connections help prevent many failures. Using custom printed circuit boards reduces wiring errors and makes testing more consistent. Environmental testing, such as exposing the prototype to different temperatures and humidity levels, can reveal vulnerabilities. Protecting components from static electricity during assembly is essential. Hardware-in-the-loop testing, where software interacts with real hardware, helps find bugs that only appear during actual use. Selecting components with tighter tolerances and following good design practices can make prototypes more reliable. By systematically addressing these factors during the prototyping and testing phases, electrical engineers can reduce unexpected behaviors. This approach leads to more dependable prototypes and smoother transitions to final production.